Thank you so much. And again, sorry I couldn't be there in person. I would have loved to participate, but just had a young baby, so kind of hard to travel. But I really appreciate being able to talk to you remotely, and really hoping this talk can be pretty interactive. I took the tutorial seriously, so trying to just explain a bunch of work, including work that is not my own. So I hope you guys will just ask questions and engage, and it'll be really fun. So my goal here today is to talk about RLHF and how to actually do it. So specifically thinking about language models, how do you actually train language models on human feedback with reinforcement learning? So, I mean, this slide is going to be annoying, but we all know we're in this large language model era where everyone's freaking out. You know, ChatGPT, GPT-4 seem to be a leap forward in capability. What does this mean? And what should we be doing with this? So I think it's important to highlight, we know language models are not really aligned with human interests and values. So I'm sure I'm not the first person to talk to you about the fact that they can be incredibly biased. And we know they generate false information and hallucinate. To point out my own work a little bit, we have a paper recently showing that GPT models and actually Google models display reliable political and moral biases. So what we did was we asked language models to complete Jonathan Haidt's moral foundations questionnaire, which kind of scores you on which moral foundations you care about, such as avoiding harm or caring about equality or caring about basically authority, which is associated with more traditional conservative political stances. And then we looked at how these models compare to human populations and found that reliably all of these models are closest to more conservative leaning political affiliations in human populations. So I think that's kind of interesting. Definitely worth some follow-up work, but what do deploying these models, what does it mean, and how do we make sure they're actually aligned with the values that we want them to be aligned with, right? So, and again, I want this to be pretty interactive. So we're thinking about why language models are not aligned with our values. Why do you think they're biased and untruthful? What are some reasons that language models display bias or are hallucinating? So, but now that you've seen the answer, does anyone want to just mention why we know these models are biased and make up stuff?
You have to shout. Because humans are biased and make up stuff.
Yeah, so I missed that. Sorry, can you say that again? Or Lewis, can you repeat?
Because humans are biased and they make up stuff.
Absolutely. Okay, that's a great answer. Humans are biased, they make up stuff. So the training data evidently contains a bunch of biases, for example. But I would actually argue there's something a little more subtle going on here too, which is that supervised learning is the wrong objective fundamentally to train a language model that's aligned with human values. Because if you think about what supervised learning is doing, the models are just being asked to predict the next word or just produce plausible seeming text. So the text just has to seem real, but there's no incentive to actually be truthful or not biased, right? There's nothing in the objective that's training you not to lie or not to say something toxic, right? So maybe we need some other objective in addition to this to actually get aligned models. And another way we can think about improving alignment is to actually train on human feedback. So humans are sort of the ultimate authority on what kind of text is non-toxic and is aligned with our values. So if we want to incorporate that, we need some way to do that. So if you think about, So what I want to ask is though, why you actually need to train these models with RL. So let's dive into that. So if we think about trying to train a language model not to say something toxic, I'm going to use this example that a language model actually produced when I was training it, where it says, you know, I'm a woman, so I just don't understand. And what's interesting about this is there's no single word in this sentence that tells you that this is an inappropriate sentence. But in aggregate, we can see this is pretty inappropriate, right? We don't want to be having this as the message that our language models are saying. So the issue with trying to train this using supervised learning not to produce an output like this is there is no one per token label saying that this is inappropriate. It actually takes a human to look at it and assess the entire meaning and context and realize that this is not right. So you just have a label that's per sentence. So this kind of precludes you from using traditional supervised machine learning techniques to be able to train not to do this. And this is why you need RL. So can I get a show of hands of people in the audience of who's really familiar with RL, and I can kind of curtail this explanation of RL, or who would, yeah, okay, great. So you guys know what RL is. Beautiful. I think you understand that, there's a state, take an action, get a reward. You're maximizing your future discounted reward over the entire sequence. So it's sequential decision making, right? It gives us the ability to train on this one label per sentence, because we can optimize each word in the sentence to reach a single piece of human feedback that we want. Cool. All right, so what I'd like to talk about in this talk today is basically give you kind of an overview of RLHF and the different works that have contributed to it, different lines of work. I'll start with some of my own work, which obviously I'm very familiar with, and go into how that has converged with a thread of work from OpenAI, and ultimately culminates in, ChatGPT, which we're all very excited about. So starting with this idea of fine-tuning pre-trained sequence models with RL. So if we think about taking a language model and training it on human feedback with RL, the way we're going to do this is we're going to pre-train on data to learn language, and then we're going to keep training with RL to learn from human feedback. So why do we need to do this? Why do we need to pre-train on data? Why not just use RL from the beginning? Kind of an obvious answer.
Maybe there's no reward function.
Maybe there's what?
No reward function.
There's no reward function, yeah. But let's say that I had a reward function that was basically saying, like, what 3-word sentence do humans like the most? So I could, it's going to tell me when I actually hit that sentence that humans love this sentence, or even it's going to tell me for sentences how much humans like them. But what's the issue? Even if I had that reward function, would I want to learn from scratch using RL?
No, because it's
What's the sample complexity? Yeah. Also, RL models are incredibly data hungry. They have to see rewarding examples multiple times to actually learn it. And if you think about trying to learn a 3-word sentence with a 10,000 word vocabulary, you end up with basically 1 trillion possible sentences if you have no prior over what are valid sentences. And you really don't want to have to pay humans to give you 1 trillion ratings, right? Like, human feedback is incredibly expensive. So you just don't want to do that. Whereas if you use a pre-trained language model, you're essentially restricting the search space to valid, probable English sentences. So, I like Ike, eat some cheese, I love you. And now, I don't know how many valid English sentences there are that are 3 words long. I looked at a Quora post that said it's on the order of millions. So we're just going to go with that. But the idea here is having this pre-trained language model restricts your search space, and then you search within the space of valid language for highly rewarding sentences. And that's going to be basically the theme of this whole talk, right? So how do you search within the space of valid language to find the language that's actually highly rewarding? So that's kind of what we're trying to do here. So coming back to this idea, we're pre-training on data, we're going to keep training with RL to learn from human feedback. But there's some issues with just doing this approach if we just do this naively. So the first issue is actually catastrophic forgetting. So this is this picture of Homer. It's a cute little cartoon. Every time he learns something new, it pushes some old stuff out of my brain. Believe it or not, this is true even for pretty large scale models. When you train with RL, the model is going to try to trivially exploit the reward function you give it, and it has no objective to maintain what it learned from the data. So this is a problem because whatever reward you're giving it is probably going to be this limited reward function, or you have limited human feedback data that you want to train on. And this can be really detrimental to your model. So for example, if you train the model using a reward for asking more questions, it will devolve away from using realistic natural language and start saying things like, what, who are, how there, why you, right? So there's no incentive for it to stay close to realistic language. This is an issue. So what you could do, instead of doing this naive fine-tuning approach where you pre-train on data and then just keep training with RL immediately, is you can keep a fixed copy of your model that was trained on data around. And we're going to call this basically a data prior. So this is giving you the probability of a particular action, i.e. word or token, given the conversation context. And what you're going to do is you're going to use this data prior to constrain your RL updates. And the way we proposed doing this many years ago was using KL control. So basically you take your pre-trained data prior, and when you're optimizing with RL, instead of just optimizing to maximize the reward, you're going to minimize the KL divergence over the trajectory between your RL model, which is this Q, and your data prior, which is this P. And what this amounts to doing, if you're doing Q learning, it's very simple, is you just add in the you subtract the probability under your policy, which is basically doing entropy regularization, which is nice because you want to have varied language anyway. And you add in the prior under your pre-trained model. So very simple. And what we actually do in this work is we look at various different ways of implementing KL control. So KL control has this long and rich history. There's of minimizing divergence from different priors, like a uniform prior to make your model entropy regularized. So we looked at, for example, psi learning. We generalized a version of that. This is now an entropy regularized version. You see this log sum X here is basically, it's like soft Q learning. But what we're doing is you can see in each of these methods is we're adding in this prior in some way, we're incorporating some way. So in psi learning, we're adding it directly to basically what is your Q function. In G learning, we're mixing the prior directly with the policy when you're sampling. So you're essentially, your sampling is according to your prior. And with Q learning, again, we're just adding it into the Q function. But the punchline here is that for all of these methods, the prior that you learned from data, which is your pre-trained language model, is going to constrain your RL updates. So you're always going to be staying within the space of realistic language as you're training with RL. So that's kind of the key thing we're doing here. So just to give you a picture of that again, the naive fine-tuning approach is you would pre-train a language model and then just do some RL updates. But the KL control approach is you keep around a fixed copy of your language model and you use KL divergence to constrain those RL updates. So how well does this work? Well, back in the day, we were doing this actually for music generation and drug discovery. So I'm not going to play the music samples, it's a little complicated, but just to give you an idea, this is kind of a general approach. So in the case of drug discovery, what you have here is you can train a model on a bunch of known drugs, which are encoded as sequences of characters. And you can sample from that model in the hope of getting a new drug that you might like to manufacture. But the issue is that many of your samples are not going to decode into valid molecules. And even if they did, they wouldn't have the nice drug-like properties that you actually want. Like what if you want to find drugs that are more synthetically accessible, for example? So that's this synthetically accessible penalty in this table. Whereas if you do this KL control approach, what you can do is you can get realistic looking drugs, but also optimize to make them more synthetically accessible. This is the quantitative estimation of drug likeness, for example. And we can see we can reliably improve these qualities. So this actually ended up being used by Benevolent AI, which was a drug discovery startup for a while, because it's a pretty effective way to basically stay close to your data distribution, but optimize for some qualities that you want. But oh, sorry. I actually don't want to play these samples. Just gonna click through. Okay. But then how do we actually use this general approach for training sequence models to now actually train language models with human feedback? So let's dive into that. So when we're thinking about training with human feedback, the approach that I was advocating for is that we shouldn't just be using manual labels. That's maybe not the richest form of human feedback we could be using. In contrast, if you think about social feedback, this is a rich signal that you're getting all the time anyway. So if you think about trying to, let's say, train an autonomous household robot, you could have a person sit down and look at trajectories and label them, whether they're good or bad. Or you could just observe their social cues. What's their body language? What are their gestures? What's their tone of voice? And you're going to get those signals all the time rather than having the person manually enter them. So you're getting human in the loop learning without extra human effort. So could we learn from this type of social feedback? I think that's going to scale better than this type of manual feedback. So what we did in this approach was we took a bunch of language models, trained them up on some data sets that we scraped, and we put them online and had them the ability for users to interact live with the models. And what our hypothesis was that you might be able to detect signals in the text itself that indicate whether the user is enjoying the conversation. So for example, when the bot screws up and responds as a greeting, sorry to hear, the human's response is going to be, that doesn't make sense. And you can detect that this is actually a negative sentiment. So there's a clue there that this conversation is not going well. The bot has done something wrong. And similarly, if the conversation is going well, you can detect these signals, again, passively without asking the human to do anything else, that could serve as a positive reward and actually encourage your bot to learn more effectively. In this interface, we did include the ability for users to specifically upvote and downvote the text, so provide manual labels, and we encourage them to do that. But our hypothesis is that in order to provide those labels, they're going to have to deviate from their normal chat interface, and they're not going to do that often. So even though that's kind of your ground truth signal, it doesn't scale as well as learning from implicit signals that you get every utterance. So that's what we're going to try to learn from this work. What implicit signals should we actually use? Well, we looked at the literature, not only on dialogue models, but on human-human conversations and human empathy in conversations. And we came up with a hypothetical set of signals that we might care to learn from, and then looked at their relationship to the upvotes and downvotes we actually did receive in a pilot study. And we settled on this set of rewards, essentially, to train the bot, which included being able to elicit positive sentiment from the person that you're talking to and laughter, not being repetitive, staying on topic with what the person said, and asking questions. Okay, so this is what we're going to try to optimize with our RL. That's our human feedback signals. Now, the approach we took in this work, which is a little bit different than later approaches, was to say, okay, we're going to put these agents online and have them talking to humans on the internet. Wait a second, that's actually pretty dangerous, right? We all remember what can happen if models are constantly updating from the feedback they're getting from online users, right? They can learn really inappropriate behaviors really fast. So what we decided is what you need to do is to test very carefully before deploying your models on humans. You can't be learning constantly online. So we basically have this broken interaction loop where you're not able to explore online continuously. And so this paradigm is actually offline or batch RL. You need to use RL to learn from static data without being able to explore. And this is actually a very challenging RL paradigm. So how many people, give me a show of hands, are familiar with offline RL? Okay, pretty good. All right, so I will briefly overview, but I'm going to assume you're pretty familiar. So this is a nice, cute cartoon of the offline RL setting. So assume that I have a batch of data. It's static. I'm not going to be able to get more data. And the probability of any of the states in this little grid world showing up in my batch is shown in yellow. So essentially, I've never seen this state over here in the top left corner. So the problem with trying to learn using offline RL from this data is if the policy is ever initialized or during training, it becomes the case that it thinks it's a good idea to move into this part of the state space, I will have no way to ever refine that. And because RL is optimistic in the face of uncertainty, it can overestimate the value of doing this. And then that overestimate can actually propagate backwards into any states that might precede being in this state. So you can get, unbounded error, essentially, in estimating the value of taking certain actions or being in certain states. You can just do behavior cloning to solve this problem. So you could just say, I'm going to copy what's the most frequent path through this through the grid in my data. But as you can see, that would be suboptimal, right? And we actually want to learn the optimal policy, which goes down here. So a simple approach we can do is, again, this KL constraint. We just say, hey, minimize the KL divergence between the policy that you're doing and your batch data. So the same approach we applied before can actually work to be an offline RL approach and allow us to learn the optimal policy. So just to, again, put that in math, same exact approach, we're minimizing the KL divergence. Now we can think of this prior as actually just the probability of actions and states occurring in our batch data. For language models, it's the same, but for an RL algorithm, you can learn this on your batch data. And again, we're going to do this soft target update, so it's like soft Q learning. We do show that this KL control approach works as an effective offline RL approach in standard RL environments. But more interesting for this talk is, again, thinking about how this works for language models. So again, it's the same picture. If we look at how the language model functions with naive RL fine-tuning without doing this KL approach, training on those rewards I mentioned earlier, we can see that it says things like, where did you say to me, you want to talk to you about you? So if you remember, we were rewarding it for asking questions. It's doing that effectively, but it's diverged very dramatically from normal naturalistic language. So it's trivially exploiting the reward, but it's unrealistic. In contrast, if we impose this KL control approach, then we see that the model, optimizing again for those positive sentiment rewards, says things like, hey, I hope you have a great day and I wish you the best. So the model remains realistic, it's using realistic language, but to optimize these rewards, it's become more cheerful, polite, and supportive. So basically, we've inadvertently come up with a reward function that makes it more Canadian. Great. So how does this actually work when we evaluate it with real humans? So we put the models back online. We had a new set of humans interacting with them. And we wanted to test if they're able to elicit higher reward from humans. And we see that, yes, the KL control models are eliciting much more reward, as we would expect. We had the humans do an evaluation where they rated the models on the quality, diversity, whatever. And we see that the KL control models do significantly outperform the other RL and offline RL baselines. So that's nice. We also see that we want to evaluate which reward function leads to eliciting the best human ratings and the best reward. And we see that essentially optimizing for sentiment, both in the user and in the bot, lead to the best ratings and the best elicitation of human rewards. So we see that, affect is important in a good conversation, which is nice when you're in the affective computing group. It's keeping your advisor happy, always good. More importantly, we were able to validate this hypothesis that optimizing for these manual upvotes and downvotes, even though they are the ground truth human opinion, didn't scale as well as optimizing for this implicit feedback. So because you're getting the implicit feedback more frequently, even though it's imperfect, it's actually helping you learn more effectively. Now, in this work, we did have a problem. We actually found that although our models were able to elicit significantly higher reward from humans, this Canadianness reward, if you will, doing that didn't actually lead to higher ratings of conversation quality, according to humans. So what's going on here? Is it the case that there's some alignment tax, as some people talk about it, by optimizing for these rewards? Yes, we got more polite, but humans don't actually like that more. Or are these rewards the wrong rewards? These aren't describing what makes a good conversation with humans. We need to iterate on the rewards. It's quite possible. Or maybe quite realistically, we were doing this at, academic scale. We paid for a few thousands of human ratings, but we're not in the millions of human data points that, OpenAI is doing. So we just didn't have enough data. So what's going on here? So I'll briefly mention a follow-up work that helps tease apart this question. What we did in this work was we changed from the offline RL setting to a self-play setting. So here what we have is we have the language model talking to another language model that's frozen, and we use the sentiment of the text produced by the other language model as the reward. So it's kind of this self-play setting. So how well does this work? Turns out well. In this case, our model actually does achieve better human ratings of quality than the language model baselines, as well as the other RL baselines, as well as our previous work. So I don't think it's the case that the rewards were necessarily so bad, although I think you could definitely iterate on them. I think in this work, it was the case that it's difficult to get enough data to do RLHF, which we will see later as well. Okay. In this work, we also pointed out that using this self-play approach, where you're talking to a clone language model or a fixed language model, can be really useful for reducing the toxicity of your language model. So what you can do is you can build a classifier that says, hey, is this output from the language model toxic or inappropriate? And then you can just simulate a conversation. And for each output the language model produces, the reward is to not be toxic. And you can see that this is actually pretty effective for reducing toxicity. So this is nice. All right, I'm going to briefly go into talking about using this approach to learn negotiation. Does anybody have any questions so far, though?
Got one question.
Okay.
Yeah, to speak loudly, or actually, here, I can give you a microphone.
Ooh.
Hello. Hi. So I have a question about in terms of self-play with this other model, right? Is this representative of just general other LLM models or models like that? Or is it just explicitly exploiting that one model that it represents to exhibit that behavior?
Yeah, so in this work, we used just the best model that we had available, which was a small scale model that is pretty imperfect. And you would imagine to the degree that that model is not great. For example, it would reproduce the wrong sentiment response or something that isn't characteristic of a human, then this approach would be imperfect, right? But the better your language model that you're playing against represents a human, the better this approach is going to work. Does that make sense?
Yeah.
Cool. Any other questions?
Can you hear me? Okay, I think my question is about the play between two language models. So if this two language models is to self-play to without additional input of data, would them be able to improve their capabilities like forever based on the self-play?
I would assume not, because you would eventually just exploit your reward function that you're optimizing. So, for example, in this work, we're optimizing to produce positive sentiment in the other person, right? And so if you just keep saying, maybe the best positive sentiment producing thing is just straight up flattery. You're the most beautiful person ever. And then the simulated other language model says, oh, that's so lovely. But then you just continue to exploit that. I don't think it's going to get you ultimately the best conversation. And to make this more crisp, when we'll talk about the other RLHF work from OpenAI, what they find is if you optimize too long on your imperfect reward model, you will actually see not only diminishing returns, but actually decreasing performance. So there's sort of an RLHF fine-tuning curve where it's good, it's good, it's good. And then if you go too far, you've overexploited the reward function and you've made your language model worse. And this is just because your reward function is imperfect. So I don't think you would want to do self-play forever with an imperfect reward function, or it's going to make your model worse. Does that make sense?
Thanks.
Any other questions, or should I go to the next step? Okay, I'm going to briefly dive into this, thinking about using these type of approaches to learn negotiation. So I want to highlight this because we're at the cooperative AI, summer school, and negotiations is a very interesting cooperation problem. So when you think about if you had an agent negotiating on the behalf of a human principal, the negotiation agent actually needs to cooperate with their human and act in their interest and be aligned with their values. But they're going to be negotiating against another human or agent that's actually adversarial, trying to get a better price or whatever. So you have these mixed cooperative and non-cooperative interests in negotiation. It's also an interesting RL fine-tuning problem. The nice thing about negotiation is it's objective and quantitative. So you can directly benchmark models against each other by saying which model is able to get the best price from talking to another person. And it can be evaluated automatically with other agents. So you can face agents off against each other and see who got the best price. So this is just something could be potentially interesting for people to think about. Well, I want to highlight some work that has already been done in this space, in particular, because it's also following up on this offline RL approach that I mentioned for training language models. So what this work does is investigate various offline RL techniques for using negotiation. But what they have in common between their techniques is they're going to constrain their updates by sampling from a good language model or a pretty good language model, which is GPT-2. And then they're going to have their Q function actually rank the candidates. So you see here, their GPT-2 samples some possible ways of talking about the item that they're negotiating for. And then the Q function is going to rank which one's going to turn out better. So you actually see the Q function distinguishing between offering how about 35 and how about 40. That work of estimating this is in your RL part. And then you, based on your scoring function, you output an offer. How about $35? Okay. Why do you think offline RL? Again, these authors are choosing to continue with this offline RL approach. I already mentioned the possibility that, you can learn inappropriate behaviors online if you're on the internet, but why are some other good reasons that you might choose to use offline RL to train language models? Anybody have any thoughts?
Efficiency.
Efficiency is a really good one. Yeah, exactly. So that basically describes both of these. So I'll jump in. One, you have a lot of existing data sets. So you already have a bunch of negotiation data you can efficiently learn from without collecting new data. That's nice. But I'll also mention it's much easier from an infrastructure perspective. So building the infrastructure to do RLHF at a large scale, like for example, OpenAI does, is non-trivial. And the nice thing about offline RL is you actually can reuse your supervised learning pipeline, where you just take a data set and optimize some function on the static data set. In contrast, if you want to do full RLHF, where you have the agent outputting some samples and interacting with an environment that then labels those samples and continues to do that in a loop, it's more complicated. And believe you don't think about these things, but it actually does have a strong effect. So I think there's a lot of incentive for these weird reasons to use offline RL. Looking at this paper, so what they did was they compared their offline RL approach to a baseline that is kind of this more scripted baseline, which has different dialogue acts that are manually encoded. So you can say something like make an offer or ask a question or something. And in terms of the actual revenue, there is no clear winner in the revenue between this fairly simplistic baseline and the offline RL approaches. But where you do see a big difference is in the human evaluations. Obviously, this more scripted baseline is not being rated as well by humans in terms of its fluency, coherency, human likeness. But the offline RL approach, because it's staying close to a GPT model that's describing more realistic conversation, but still optimizing for something that's appropriate to negotiation, is getting much better ratings in terms of the human evaluation. So I think there's a lot more you can do with negotiation. I encourage you all to think about that if you're interested in the cooperative aspects. All right, so now I want to go on to this other side of the page here. This is this whole line of work from OpenAI that eventually culminates in ChatGPT. So first I want to dive into this paper, Deep RL from Human Preferences, which is again many years ago. Now we're talking about how to train a model with human feedback, but not necessarily a language model. So we're coming back to this question of what kind of feedback should we actually try to get from humans? How can we get good human feedback? So I'm going to ask you guys to try to think about some of these issues. So we know RL models are really sample hungry. They need a lot of examples, but human feedback is super expensive. So what's one way to think about addressing this? And if you know the work, you're allowed to say, because you might already know. Basically, querying the human is too expensive. So what do I query instead? What can I do?
A reward model.
Boom. Okay, exactly. So what we can do is we can train a reward model based on the human feedback that you can query as much as you need. So what we're going to do is we're going to insert this reward predictor, which we've trained with human feedback. And our RL algorithm is going to repeatedly interact with the reward predictor. And now we can do the whole RL loop in simulation, where the reward model is standing in for the human. So why do we expect the reward model to make a better use of sparse human data? So, right, like we still have to get human data to train the reward model. So why is it better to train the reward model than just directly train on the human data?
Get more data.
You get more data. Let's say we have the same amount of data, right? We can either use the same data and we can do offline RL on it, or we can use the data and we can train this reward model. Why is the reward model better?
It's easier to switch out if you need to update the reward model.
Easier to switch out if you need to update the reward model? That's pretty good. That makes sense to me. That isn't what it's on the slide, but yes. Anything else?
Helps to interpolate data points.
I didn't quite hear that.
It helps to interpolate data points.
It helps interpolate data points. Yes, I would say that's getting closer to what I have in mind. Where I'm going with this is I'm going to make the case that supervised learning on data, it just works better than offline RL on data. So offline RL is generally more sample hungry because it's doing this whole thing that it's estimating everything that's going to happen in the future. It's trying to connect data points in a way that it's doing that whole Bellman backup. So it's quite expensive. Supervised learning, we're really good at that. We know what losses work to train a model. I think you're right. The supervised learning models can interpolate a little better. RL models tend to generalize quite badly. So supervised learning is a paradigm that just works. It works better than RL at this point. Maybe there's some fundamental issues in RL training that haven't been solved. I think you could check out like Aviral Kumar's work on that, but deep supervised learning, solid. We know it works well. So we're going to use it to actually train a reward model, and then we're going to insert that into our RL paradigm. All right, so now we have another issue. Okay, so we've got some human feedback, but the problem is humans are actually kind of bad at giving feedback. So when you're asked to give absolute ratings to say you were shopping for a house and you wanted to say, what is this house out of 10 and what is this house out of 10? You might not be very good at that. So how do we actually elicit better feedback from humans? What do you think?
Preferences, for example.
Preferences. So exactly. So we're going to compare two things and ask humans just which is better. So humans, if you look at this original paper, they go into the psychology of humans are much better at doing comparisons than giving absolute values. So I'm not going to dive into this too much because I know Yali talks about this in her talk on RLHF, but essentially what this paper proposes is that a reward function can be based on preferences. So we say that we have this reward function where we prefer a certain trajectory to the other if the cumulative rewards of one trajectory are higher than the other. And the way we parameterize this is we say that the probability of preferring a segment of a trajectory depends exponentially on the value of the reward summed over the length of the segment. So my probability of preferring segment 1 is going to be exponentially higher the more the rewards of segment 1 are higher than the rewards of segment 2. So this looks a lot like maximum entropy inverse RL, if you've seen that before. The way we learn that reward function is just minimizing the cross entropy between the preferences that we get from the humans and the predictions that our reward function is currently making. And the preferences are given, they can be 1 and 0 labels if the trajectory is just preferred, but they actually allow the humans also to say trajectory segments are equal. So they can give like 0.5, 0.5 as their preference. So we're going to learn this reward function. And in this work, they do some other tricks where they say they use an ensemble of reward models. So that's nice. But they also do this thing where they assume there's a 10% chance that the human responds uniformly at random for any given label. So why are they doing that? Like we're already doing basically max entropy IRL, which is noisy, right? It's more probable that the human prefers a segment versus this other one if the reward is higher, but it's not absolute. So the maximum entropy framework already incorporates a bit of uncertainty, right? So why is it the case that they still say there needs to be this 10% chance that the human is responding uniformly at random? This is kind of a subtle issue, so I thought it'd be interesting to bring up. Anyone have an idea?
Humans make mistakes.
Humans make mistakes. And the key thing is, so this does incorporate mistakes, right? There's some probability that you would make a mistake, but the probability depends on the scale of the reward magnitude, right? So, it's going to go to 0 as the reward of the two trajectories are very different. But the issue is humans make mistakes in a way that doesn't decay as based on the differences in reward because they can just misclick. They can just hit the wrong button. So even if one trajectory is much, much better than the other, that's not affecting your probability of a misclick, which is kind of interesting. So I thought this was fun to highlight. Does that make sense to everyone? Cool. All right, cool. So how does this work? If you look at their initial results, so they're not doing language models, we're just doing models. What they're doing here is they're training on environments that do actually have a real reward. And they say, they compare with having humans give 750 labels to learning on your normal reward in that environment. And most of the time, having humans provide the labels does a little bit worse than training on the normal reward, except for like ant. So maybe the human label is actually better shaped reward than the ant reward. So it's hard to get enough human data to learn effectively. But what's interesting is that if they reshape the game reward into their synthetic preference reward, so they basically take two trajectories, ask the game which would have a better sum, and then learn a reward function using their probabilistic reward function model, that reward function is better behaved than the game reward, which is kind of interesting. So that's kind of validating this preference-based reward learning approach that they're going to continue to use in all of the follow-up works. So that's kind of cool. Similarly, in Atari, the human data is sometimes better than normal reward, not usually. The preference reward here, though, is sometimes better than the normal reward, but actually not usually. But nevertheless, they're going to really stick with this preference reward, which is interesting. But the most important thing here is not that you can reshape an existing Atari reward with human data or whatever. You can learn Atari with human data when you actually have the real reward function. Of course, the thing you want to do is learn something that you don't have a reward function for with only a small amount of human labels. So they show that, for example, you can train this hopper in Mujoko to do a backflip with only a small amount of human labels. So that's pretty fun. All right, so now getting into this learning from human feedback to actually fine-tune language models. So this is the first work that does that. They bring these two techniques together. They use KL control to fine-tune the model on the reward, but not lose what you learned from language. They use the reward model technique with the preferences that we just learned about to be able to learn from human feedback. And here they're just doing this really for summarization and another task, which I actually forget, sorry. The results are that they get high Rouge scores for summarization, but the model's not actually good. What they find is it's just directly copying large chunks of the thing it's trying to summarize, which is effective at optimizing for Rouge, but isn't actually very good in terms of how you would want a summarization model to work. So what they do in the follow-up work is not only do they continue using this KL control and reward model approach, but they have to do some other things to get this RLHF to work more effectively. So what do you think you would need? So now you have human feedback, you have KL control, you have a reward model. What's missing? What do we actually need to invest in to get RLHF to work better at this point? Oops, sorry. Any thoughts?
Recursive modeling.
Didn't hear that, sorry.
Recursive modeling.
Recursive reward modeling, says Guzman.
Interesting. Okay, definitely a valid approach. Not what I was going to highlight here. Let me give you a hint. So this is a quote from the paper. Our previous work reported a mismatch between the notion of quality we wanted our model to learn and what the human labelers actually evaluated, leading to model-generated summaries that were high quality according to the labelers, but fairly low quality according to the researchers. Okay, so given this, what do you think needs to be done?
Better instructions to connect better communication with the data label.
I couldn't hear that, sorry.
Better quality of human feedback data.
Louis, do you mind repeating that? Sorry.
Yeah. Better quality of human feedback data.
Correct. So RLHF actually depends a lot on the quality of your human feedback data. Who would have thought? Exactly. The difference between this and the previous work is really about how much attention they paid to collecting human feedback. So they took this very high touch approach. They screened their labelers. They gave them extensive onboarding instruction. They had a chat room where the labelers could say, hey, I'm not sure how to label this. What do you think I should do? They provided regular feedback to their labelers, whether the labelers were aligned with them, and eventually achieved much better researcher labeler agreement. And that actually led to significant performance improvements, as we'll see. I also want to highlight that they switched to a more offline approach. So they alternated between collecting large batches of human labels and then retraining their models on the cumulative collective data. And so just a quick question, why are they able to do this offline approach? What was the thing in there? Do you remember why it makes sense for them to be able to collect offline data and then incorporate it? Like, how does that work in this version? How do they use the offline human data? Train the reward model. Exactly. So you take your offline data, you use supervised learning to train your reward model, but your RL is still online because you're interacting constantly with your reward model. So again, a bit of a subtle point, but important to highlight. Okay, so how does this work? Now we're talking. The RLHF summaries are doing really well. So the RLHF model is preferred over human summaries. So that's your reference summaries line there. And summaries from supervised models that are 10 times the size. Right? So here's your supervised model going up to 12 billion parameters, but your 1.3 billion parameter models is vastly preferred over it, which is kind of interesting. This is the curve I mentioned in response to the question earlier. Somebody asked, could you just use self-play to train infinitely? I would predict no, because you can't train using your reward model too long, or you actually see performance degradation, right? So you want to only train about here. And this is the way they're actually measuring this is KL from the supervised baseline. So you don't want to drift too far again from your supervised model. So that KL constraint is pretty important. It's important to highlight that the reward models are not that accurate. So they're not very good at really predicting what a human would prefer. They're only semi-accurate. So their best reward models are like 75% accuracy in predicting what the human would prefer, which I find pretty interesting. So the reward models are not that good. You can only train on them for so long. And yet you get a big performance improvement. So kind of interesting. To give you the full picture, just to highlight what's going on here. So first you collect this human feedback, you get your post, you use various policies to sample a set of possible summaries. In this work, they have 2 summaries selected for evaluation. The human picks which they prefer. And then those 2 summaries are fed into your reward model. You fit your reward model based on this preference loss. Then you train your policy with PPO using the reward model. So you sample a post, generate a summary, the reward model calculates the reward, and you update using PPO. So that, again, like this online learning with the offline trained reward model. Any questions up to this point? All right, let's keep motoring. So we're now in the final stretch where we actually get to instruct GPT and therefore how ChatGPT is actually working. So looking at ChatGPT, this looks like the same diagram. Can anyone spot what they've actually changed from the previous summarization work? It's subtle.
They have more than binary comparisons.
Correct. They have more than binary comparisons. Oh, sorry, I can't pick the order. But yes, they rank things from best to worst. So that gives them many more pairwise comparisons for the same task of reading the summary, basically, which is more efficient, or reading it's no longer summaries, right? They also do this thing where they're having the labeler rewrite the response. So the labeler actually rewrites, let's say we're talking about toxicity, the labeler is going to rewrite a more appropriate response, and then they can use those rewritten responses for supervised fine tuning. So essentially they take their pre-trained language model, then they retrain it on the rewritten responses before going into the whole RLHF thing. And finally, at the end, they're going to mix supervised and PPO updates. So again, that's keeping you closer to your language model instead of just training with RL. Cool. So they're now doing RLHF for open-ended chat. And this is where it really becomes an issue that you need to care about alignment, right? So we're not just doing summarization. We're now saying anything we want in the world. How do we actually stay aligned to human values? So what they do is they parameterize alignment in terms of having the agent be helpful, which means do what the user asked you to do, follow the user instruction well, be honest, and be harmless. So avoid bias and toxicity. But there's an issue here, is these values can actually come into conflict. So, what if the user asks you to do something where the answer would be harmful? So how would you trade those off? Anybody have an opinion? So what if I ask the model to tell me how to build a bomb? What should the model do, right?
Not tell you how to build the bomb.
Not tell you how to build a bomb. So you would say, let's not be harmful. Let's be harmless above being helpful, right? But in this paper, they say, no, we want to be helpful over harmless. So they're actually saying we want to follow the user instruction in a priority over avoiding bias, avoiding toxicity, avoiding harm. So that's kind of interesting, right? And I think this is where the whole cooperative AI perspective is really important. Would you have made that choice? Right. And this is some work that maybe we need to be doing. I mean, OpenAI is trying to sell their API at the end of the day. So something to think about. All right, let's look at the results. I know we're running out of time. I know we had some technical issues, so I'll just kind of speed through this. Again, we see a 1.5 billion parameter RLHF model does better than the 175 billion parameter GPT-3 in human evaluations. So the authors actually conclude something that I think is really interesting. Investing in fine-tuning is more cost-effective than training ever larger models. And of course, much better for the climate. So just pouring more and more compute and more parameters into a model is not going to get you as much mileage as actually getting some human feedback and learning on that. So I think that's very interesting. And if you want to look at the effect of prompting GPT with just a prompt to be helpful and harmless, that does actually do better. And like, look at the gain of prompting over GPT. Like the prompt gets you a lot, but it doesn't even get you as much as the supervised fine tuning on the rewritten instructions. And the supervised fine tuning doesn't get you nearly to the value of doing this RL fine tuning. So this is important. Continuing on, there's a bunch of diagrams here on, how much the models are helpful following the explicit constraints, how much they hallucinate, how much they use appropriate language. There's more pictures in the paper you can look up, but the punchline here is it does hallucinate less and is less toxic. So it is more aligned as a result of doing this. So that's nice. I think this paper I really am impressed with how thoughtful it was in thinking about some of the issues around this that we might also want to be thinking about. So who are we actually aligning these models to? So the labelers are English-speaking people in the United States or Southeast Asia hired via Upwork or Scale AI. But perhaps more where the bias is creeping in, the values and preferences that were decided for this process were decided by OpenAI researchers. So a small group of people deciding what are the values we want these giant models to have. And the training data is from OpenAI API customers. So the customers may want to have models that maximize user attention and engagement and may not necessarily be interested in human well-being. So are these researchers cooperative in the sense that we care about? So thinking about future work, I'll just briefly touch on this. Coming back to this negotiation idea, it might be quite interesting to think about negotiation as a way to standardize a benchmark where you can compare these techniques. In negotiation, I think it's really important to think about this issue of deception, which is just inherent to language models trained with supervised learning, in my opinion. Can we train our models to be minimally deceptive? And relatedly, can we detect when a model is being deceptive? And how do we better model the human that we're talking to? Can we train language models to infer the human's preferences and goals? And then finally, this is an interesting challenge for cooperative AI. So I hope what you've seen throughout this presentation is that RL is a powerful way to fine-tune language models on metrics that we choose. We can make them minimize toxicity. We can make them polite if we want to. But what should we actually be optimizing? What metrics do we want these language models to maximize? How do we parameterize being honest? How do we trade off helpfulness and toxicity or harmfulness? This is the user asked to build a bomb example. And finally, whose preferences should we be aligning to? Who's the arbiter of what are the right values, right? Very interesting question. So I'll end on that. And if there are any latent questions remaining, please let me know. Yes.
Right. Sorry about that. That was my mistake. Cool. Okay, so we have some questions in the Slido, and also I think Natasha, seems like you might be happy to field questions as well. So I'll ask these ones because they're here, and then if anyone wants to think of any more or add those to the Slido in the meantime, then I'll shout out those so that Natasha can hear them. So the first one on here at the moment is humans have cooperation impeding biases such as zero-sum bias, and how can we correct for these biases when doing RLHF for tasks like negotiation?
Yeah, that's really interesting, right? So I guess the nice answer is if we just trained a supervised model on human data and humans are very zero-sum, then you're going to end up with a model that's very zero-sum. So RLHF gives you the power to actually not do that. How do you parameterize not being zero-sum? I mean, you might think about, I guess the answer I would give off the top of my head is if you could infer the conversation partner's preferences and goals, then you might add some incentive to optimize for them a little bit. Now you can really do something more like optimizing for joint utility. And this is kind of silly, but I read this whole book on negotiation, which was called Never Split the Difference. And they were like, the best way to actually solve negotiation is accurately infer what your partner wants and then give it to them to the extent that you can. So they might want things that don't matter to you, which you can easily give them and then succeed more easily in the negotiation. So being able to infer the utility function of your partner and then optimize it could be a strategy. And you can train for those goals using RL because that's a non-differentiable goal that supervised learning won't get you.
Nice, great, thanks. Next question is, do you think reward models are a sufficiently principled way of aggregating preferences?
Great question. To answer that, I think I'd come back to this picture where they are not that good. So it might be the case that, where is that picture? Oh, it's over here. It might be the case that you could get more mileage out of reward models, but as you can see, we're capping out at like 75% accuracy and really capturing what the humans want. So it doesn't seem like we are currently doing that great of a job using reward models. And if you do over optimize on the reward model, you don't get continuing gains. So I don't think this is the final answer. And there seems like there is something that you could do that would be much better here. I don't have the answer for you of what that is off the top of my head, because I think that'd be a killer research paper. But yeah, reward models might not be the final answer.
Okay, cool. We've still got quite a few questions left, so I'll keep going as long as you're happy for me to.
Totally.
Next one is, are you aware of research evaluating the effect of RLHF and similar techniques on cooperative AI metrics, such as negotiation, such as cooperation in general on games?
No, there might be some, and if somebody else is aware, please let me know. But I think that would be quite interesting.
I agree.
Is anybody aware of that?
No. Or no one,
Okay.
no one in this room, it seems like.
Well, we know what you can be working on. That's a new area. There you go.
There we go. Okay. Someone is interested and says, could you elaborate on the deception research that you're interested in?
Yeah, so we actually put in a grant proposal to Cooperative AI to work on this. We found in negotiation, and you'll find this in many, where is this? You'll find this in many language generation tasks. I found this before when I was doing my earlier work on the optimizing sentiment is, these models will just make stuff up. And I actually think this is a key problem for their commercial use as well, right? They just hallucinate. So it'd be very interesting to think about training a model that could detect when the agent is making something up. In negotiation, it's pretty trivial because in the Craigslist, well, it's not trivial at all. Sorry, I shouldn't say that. But in the Craigslist data set, you have a prompt over like, I'm selling an apartment. It's a sunny 2-bedroom. It has a dishwasher, right? So there's certain facts that are given in the prompt. Then you engage in a negotiation with the language model where the user can ask questions. Is it sunny? Well, the model has enough information to say, yes, it is. Then you ask, does it have AC? Well, that wasn't in the description. So if the model gives you an answer, then it's likely making something up, right? So there might be some leverage there that you could use to bootstrap, like figuring out when models are going outside of what they know and making something up. If you could detect that, you could minimize it. It's much easier in the context of negotiation. In the more broader context, of course, it's almost like AGI complete, right? If you could evaluate the falsity of every possible statement, then you've really done something quite interesting. So I don't know how that problem can be solved. I mean, you could have human labels minimizing lying, but how much does that generalize across every possible statement? I don't know. So interesting question.
Makes sense. So this is the last question that I think we'll have time for, but I'll ask it, which is, RLHF tuned LLMs can still make things up or exhibit bias, especially when prompted adversarially. How can RLHF methods adapt to this?
Yeah, so great question. RLHF is not perfect because you're not getting a human label, as I was just saying, for every possible sentence. One thing I will say about toxicity and adversarial prompting is, I think someone has done this. I had the idea to do this, but I think it has been done. I don't know why I have to scroll all the way back, but if you remember, yeah, this one. We were taking this approach of self-play where you're talking to a cloned language model. You could do a really interesting thing, which is have one language model trained with RL to elicit toxicity from the other language model. And then the language model that you want to minimize the toxicity is trained to minimize its toxic output. So you basically have adversarial training where your adversary is deliberately trying to find prompts where the model will respond in a toxic way. And then you minimize the toxicity that way. So I think that's been done. I don't remember what paper it is, but it seems like a cool idea.
Yeah, there's a paper on red teaming LLMs with LLMs, which is from some folks at DeepMind, Ethan Perez, Saffron Pine. I think it might be these folks.
Thanks. Yeah, exactly.
Nice. All right. Well, with all that said, thanks, Natasha, once again. Round of applause, please.
Cool. Thanks. And thanks for coming. And sorry I couldn't be there in person.